Welcome back. To those of you watching the video on the road, I am setting up a problem so that the second people walk in before class starts, I want them to start working on a problem. So that's what's going on here. If you would try to work through the following and pause it, that would be awesome. Okay, here's the example that I want you guys watching the video to go ahead and start. Pause the video, and when you're done, resume it. You'll see or hear our class working through a detailed solution. Cool. Pause it, and you can resume in 3, 2, 1. All right, so if we're looking at this problem, I'm not going to make you guys do it independently, although I have faith that several of you, if not all, some, I don't know, maybe none, who knows. But you guys have seen this. My first question is, in the quadratic formula that is in that lovely song, or the dull version of it, which is one that I prefer, what are A and B and C representing? Like, where do I get the values A, B, and C to plug in? Somebody knows. I don't want to pick on somebody who doesn't. Anybody want to volunteer the answer before I pick on somebody who might not know? Fern, we made eye contact. Do you know where I get A and B and C to plug into the quadratic formula? So, love the language. I would refer to them as coefficients, but you're okay. Remember, this thing is all a result of ax squared plus bx plus c. This is where these numbers come from. Now, in this situation, I'm asking you to find all the roots of this polynomial that happens to be a quadratic. Quick check here. What's its degree? How many roots do you think we're going to find? 2. We better find 2 of them. They might be repeated, which that's fine if it happens, but they might not be. Before you jump immediately to the quadratic formula, which if you guys learned it in Algebra 1, I don't recall, but in Algebra 2, what I always saw is the second somebody learns a quadratic formula is every other way of factoring is gone because a quadratic formula is plug and chug. Before you do this, though, you should always check everything else. I claim grouping won't work. Do you agree with that statement? And how do I check to see if grouping will work for factoring this quadratic? Louder. So GCF, there isn't one, so that's the first thing I always check. There's no coefficient of 1, which means a shortcut's not available. You do not have to write this. If you want to check it, we can see grouping fails, but here's the check. If you do 7 times 2, what do you get? 14. Find me 2 numbers that multiply to be positive 14 and add up to 5. It's not 1 and 14. It's not 2 and 7, although that one feels like it might work. But you would have to have positive 7 and negative 2, which would make a product of negative 14, and it breaks. It's also not 7 and 2, and it's not 14 and 1. None of them work, right? Now, in this situation, it doesn't mean that there aren't any roots. It just means that maybe our roots don't live in the form of a nice number, which is what's going to happen. So, when we encounter this, with regard or as an extension from yesterday's stuff, we have to deal with some other stuff. So here we go. X equals, in this situation, I don't always make people do this, but help me real quick. I wish I had an easier way to change colors quickly. What's A in this problem? 7. What's B in this problem? 5. And what is C in this problem? C is 2. 7, 5, and 2. And it has to be in order, right? X squared, X, and then the constant. So let's just kind of rock through this and see what it shakes out. Or what shakes out. That was a weird way to word it. Here we go. X equals, let's see here. Negative B would be what? Negative 5. So here we go. Negative 5 plus or minus, because it's going to be both of them, the square root of, I'm going to write it out all the way first. This is 5 squared minus 4 times what? A is 7 times what? 2. And all of this gets divided by what? 2a, which is 2 times 2. Okay. Thank you for that. 2 times 7. I was stressing because I immediately abandoned the thought of trying to switch colors for every single piece. Just, I don't want to do it this time. All right. If you would write exactly this, that's fine. more realistically, I'll show you, like all of our mental math is at different degrees. I'll show you what I would normally write just as my first step. It's going to be all the same pieces, but I clean up a little bit. If I were doing this problem myself, I would have -5 plus or minus. My first step would be this, 25 minus, and let's do some thinking here. 4 times 2 is what? And I'm rearranging in my head. Times 7. 56. All over what number? 14. This would be the first thing that I would write, most likely. Now, if there were a bunch of negatives and stuff, I'd be wary of that, because even I make mistakes when you're doing negative stuff. Like, it happens. Any part of this that you look at and go, ooh, what? Or why? Or where? Or how? Good question. The Cowboys did win last weekend. Okay, as we go through then, let's go to our next step. We get -5 plus or minus something. How do you guys do this subtraction? Like, because I imagine you're not going to do long subtraction on a piece of paper. When you guys encounter this, 25 minus 56, how do you do it in your head, Abigail? And then you make the answer negative. Okay, so 56 minus 20 is 36. Minus 5 more is 31, but it's negative. Okay, this is -5 plus or minus the square root of 31. Still all divided by what? Sorry, -31. And it's all divided by 14 still. Now, just some language that at this point isn't hugely important. We refer to one part of the quadratic formula as a very important term because it tells us what sort of roots we're expecting. The thing that we take the square root of, the radicand in our quadratic formula, is known as the discriminant. Not discriminate, the discriminant. Okay, right now my discriminant, after we've simplified, is what? -31. The radicand in my quadratic formula is called the discriminant. It is -31. The fact that I have to take the square root of that tells me that my roots are going to live within which number set? Complexes, because immediately I only have one step left. 31 was a nice number because I can't break it down into squares. What does come out of this, though? I can do one little simplification. I'm not going to keep the square root of -31. Not a chance. Give me two numbers and multiply to be -31. -1 and 31 will do it, right? You could do -31 and 1, but I like the first answer. Why do I want to focus on the fact that -1, that times 31 is what we get? It's I. -5 plus or minus I times the square root of 31, all divided by 14. Okay. Quick check. How many roots did we just find? 2 of them. On a graph, what will they look like? That's a bigger check. Let's check. Okay, I'm going to need somebody to read this to me because there's not a chance that I'm going to be able to go to Desmos and remember what this is. 7x squared plus 5x plus 2. Okay, I'll come back to the screen in just a second, okay? So let's see here. Already gone. Right away it's gone. What was F? Okay. Now, this is where things get wonky. And I want to see if, just mathematically, if we can make sense of it. We think of roots or zeros as the whats of a graph. Root zero solutions, there's one more word that we normally see. So I've already said solutions, specifically with a graph. The x-intercepts. How many times do you see this parabola cross the x-axis? But how many roots did we just find? What? Why? How? What? How does this work? Why is it not showing up here? They're imaginary. We are graphing with real numbers right here. We have a real x-axis and a real y-axis. Did you guys last year graph imaginary numbers? Where you'll have a real axis, be your x-axis, and bi winds up being your vertical axis. So they just wind up being points. Maybe, maybe not. Okay, regardless, If you did, cool, we'll see it again. We don't see the roots, but are they there? They just don't live in the real numbers, which is what we see on the board. Okay, quadratic formula stuff. Yay or nay? Prove it. I got one more for you. Last possible example of the entire section. Example B, and I'll keep yellow here. I want you guys to find me the roots of this lovely function. Can I throw you a curveball and just see how you react? I'm going to. Check it out. F of x is pretty standard. What about z of phi? Z of phi, we are told, is 8 phi squared plus 14 phi plus 9. What the phi? It's a Greek letter. It's like theta, but the other way. You might hear it pronounced as phi, but it just, for real, I think faux fum every single time. This is a Greek letter. This actually represents the golden ratio. For anybody who's ever heard of the golden ratio, phi is usually used for it. Does this change anything about the problem other than the letters that you write? Is anybody looking at this going, Holloway, that's the dumbest thing I've ever seen. I'm just going to use x. I don't believe you guys. Somebody's going to. If you make that change, I totally get it. But make it a habit. If I give you wonky stuff like this, I'm just trying to make sure we don't always associate f and x because it can change. If you want to make the change, I'll allow it, but you need one extra little requirement. If you're going to make the change, you need to indicate it somewhere. If you just do let phi equal x, you can make that change and replace every phi with an x along the way. This statement is required though, because if you just all of a sudden start doing it with x and f and all that stuff, then there's an issue. And like realistically, I'd be able to follow it, but in a realistic context where maybe you have 2 or 3 functions representing different stuff, you don't want to mix your stuff up. Cool. I'm going to give you guys a second. I'm going to pause it. If you guys are watching this on the road, go ahead and pause it now, work through this, and you will see a detailed solution in 3, 2, 1. You probably got to this point at somewhere in your problem. If you stopped here, you would not get full credit, but you also would get some credit. You get most of your credit because your answer is pretty good. The rest of this is that simplifying idea. Okay, going through, help me break this down just a couple little steps to see if we can make it a little bit nicer. This is equal to negative 14 plus or minus. What's going to come out of the radicand? A 2, because we're going to take the square root of 4, right? So a 2 is going to go out front, and it's going to multiply by the I. I'm going to do it like this, so it looks normal. Root 23, and then I'm going to do one more step in this process. When we have answers that are going to be of the complex form, they should look like a plus or minus, in that case, bi, which means a very clear a value and a very clear b value as well. Am I allowed to do this? When we want fractions to add, we just need a common denominator, and we just stick everything over the common denominator. Now, if we can identify this next step is so easy. What goes into both of these? Or if you'd rather, we could say, how does this fraction simplify? But I don't know which language is easier for you. Probably the second. How does 14/16 simplify? So we get negative 7/8 plus or minus. And then this, we don't have the risk of it happening. This 16 is only allowed to divide out or simplify with which part of my numerator? If this were a 16 in here, which would be odd because it would be a nice number, but can you ever simplify the denominator with stuff that's inside your radical? Not allowed. Can't do it. So the only other option, I don't think I is going to simplify with 16, but does 2/16 simplify? How? 1/8. So it is entirely up to you. I would write this letter, or this as I root 23 over 8. This is how I would write it. Me personally, I think that if you want to, you can, and it's probably more correct. It's equally as correct, but I'll tell you, I don't like this notation. Could we call it this instead? I'm wary. They're the same thing. I am very concerned about doing it this way only because I'm concerned about your radical symbol extending over it and just notation getting confused. This is the answer that I prefer. I would still call this standard form because it's A plus BI, but we have them both. Okay. Which one do you guys prefer, option 1 or option 2? Everybody prefer 1? Sick. Cool. All right. We are halfway through the chapter. Y'all ready for the quiz? Probably not, which is okay because we talked about that yesterday. Hopefully that didn't stress anybody out too much. We have an assignment that I want you to get working on. And we've done quite a bit of stuff in here. Remember, all of this is with complex numbers within addition or multiplication, division, those sorts of things. I want you to do the following assignment. And it's going to seem long, but we have 25 minutes right now. And I will put it on here, I suppose. That's going to be obnoxious, and that's okay. Okay, for tonight, this weekend, right now, you get homework 2.4. You're going to find this on page 152, at least starting on page 152. Oh my gosh, I regret this decision immediately. I'm going to have you guys wait for one moment before you start because we're just going to do the vocab together. But I want you to do numbers 7, 11, 35, 39 through 45 odd. Yep, super regretting it because I'm going to have to. And then let's say 55 and 69. 55, 69. Okay, quick reminder. Have we ever talked about this? What's calcchat.com? It's more than just the answers, though, because the back of your book has the answers. This gives you answers and a solution. Okay, it shows the work, right? Use this if you need it, or come to me for help. I'll help out. Here's the homework. We're going to have a bunch of time to start on it. Before I let you guys start, though, we're going to do a class-wide vocab from this section. I think that's just as good as assigning you the problems. If you want to read these, they're on page 152, your text. We're going to look at 1 through 6 together, but we're just going to talk them out. Cool. So I'll give everybody a minute. Sean, go to page 152 so you can see these. All right. For number 1, we have a blank number. Has the form A plus BI, where A is not 0, but B is. So it's just A plus 0I is what it winds up being. What sort of number do you have? Whoa, I just spit a bunch. Whoops. If it's, you're not wrong, but it can be smaller than the complexes. If there's no I, it's real. These are the real numbers. Now, if you answer complex, you're not wrong. It's just not the best answer. Because every integer is also a real number, but integers is a more specific answer. Okay, number 2 on page 152. A blank number has the form A plus BI, where neither of them are 0. I would call this complex. Just so you know, your book uses the word imaginary, but I despise it so much that I just call all these numbers complex. Complex numbers are complex numbers. Okay, imaginary is also fine, but there's a reason I don't use it. Number 3, what sort of number is it? Just A equals 0, so it's 5i, for example. It is still complex, but there's a better answer. More specific, you're closer. That is my imaginary, but it's my pure imaginary. There is no real part to it. The pure imaginary number, if it's just an I. Okay, number 4, the imaginary unit I, hate it so much, is defined as the square root of what? -1, and that means that very specifically I squared gives you -1. All right. Sean, when A is a positive real number, the blank root of -A is I root A, and I changed the order. This is number 5. we're taking a positive real number, which means negative a is guaranteed to be a negative number. So you're close. If you take a square root, you get plus or minus. What's the word that we use if we only deal with the positive one? P is for positive, and Ms. Morris, who is our principal square root, is the positive version. So 90% of the time when I say what's the square root of a number, you guys give me the principal root. All right, last one. A plus bi and a minus bi, when compared to one another, are what's? Makes me think of jail, but that's probably not an appropriate comment. Conjugates. Complex conjugates. Cool. All right. I want you guys to work on this. I will pass out note cards here in a minute. Are we doing a... Does this chapter feel hard so far? Okay. I'll pass out note cards. Hopefully the note card is all you have for homework. All right. I'm sorry to do this to you again, but I cannot get anything but Fall Out Boy out of my head. So we're just going to listen to Fall Out Boy until it stops playing. Cool. Filipino fun fact, real quick. I've never seen one. You guys ever seen a tarsier? I've never seen one. They are only alive in one small region of our planet. Any guesses? It's the Philippines. I believe these are smallest primates. Yep. Gosh, they're cool. Look at them opposable thumbs. I mean, you can't see them, but I know they're there. Gosh, what a cool guy. All right. You have fun.